In studying the waves produced by light, we can see the wave here. In studying the wave and measuring wavelength, the distance between two crests, and it was measured in meters, nanometers, and in looking at frequency, which is the number of waves that pass a given point per unit time, scientists realized that there was a correlation between wavelength and frequency. And by the way, again, this is the symbol for wavelength. And this, the Greek letter nu, is the symbol for frequency. And scientists realize that as wavelength increased, the length of the wavelength increased, the frequency would decrease, and that wavelength and frequency were inversely proportional. And they realized that in a vacuum, a light travels at the same speed. And this is assigned the symbol c. And the speed of light will be, it's a constant, 3.00 times 10 to the 8th meters per second. So they developed this equation. By the way, frequency, as stated before, is measured in seconds. So the number of waves that pass a given point per second. And therefore, since it's per second, it may be written like this, or seconds like this, which is equal to hertz. So the unit for frequency is hertz. In scientists noticing that wavelength times frequency is equal to the speed of light, then we can use any form of this equation. That is, if I am given, let's say, wavelength, if that is my given, and I am looking for frequency, I can say that frequency is the speed of light over wavelength. And the speed of light is always going to be 3.00 times 10 to the 8th meters per second. Realize that we can use any form of this equation. However, the light as a wave theory or idea did not explain all the question. And a question that was left unanswered was, why is it that heated objects will change color emitted depending on its temperature? For example, if you heat iron is going to turn first a reddish color, and then after a while, after the temperature increases, it will turn orange. Why is it that a metal is going to change to a different color? Another question is, metals will emit electrons when light of a specific frequency is shined on it. So in order to answer this question, we need to look at the dual nature of an electron, that it will act as in the form of a wave and in the form of a particle. So we look at the dual nature of wave-like, particle-like. In the midst of all this questioning, along comes a scientist by the name of Max Planck, and he states, matter can gain or lose energy in small, specific amounts that he refers to as a quanta. And a quantum of energy is a packet of energy that can be gained or lost by an atom. So when we talk about, let's say, iron, being heated, and it first turns a red color, and then it's going to turn an orangey color as it gains more energy. What he is saying is, if we look at the color red has long wavelength, okay, long wavelength. That means it has a low frequency, and once it turns orangey in color, orange, you will see that will have a shorter wavelength, higher frequency, and therefore more energy. So Max Planck comes up with an equation, and his equation is energy is equal to Planck's constant times frequency. This is a constant, and the constant for Planck's constant is 6.626 times 10 to the negative 34 joules times second. So he is relating frequency to energy. So he's saying the shorter the wavelength, the higher the frequency, and the higher the energy. The longer the wavelength, the lower the energy. So long wavelength equals to low frequency, and low frequency equals to low energy. So frequency and energy are directly proportional. Again, long wavelength, for example here, long wavelength will be equal to low frequency, which is equal to low energy. Now, short wavelength is equal to high frequency, so you have more waves passing this point per unit time, which means that the energy is greater. Planck also realized that if you shine, for example here, if you shine a light of a specific wavelength, let's say red, on a metal, red, remember, has long wavelength, low energy, therefore it doesn't have sufficient energy to cause an electron to be released by a metal. So in red, an electron is not released by a metal. But if we shine blue or violet, green, violet, blue, higher frequency light onto a metal surface, an electron will be released by that element. That causes that dual nature, particle-like, wave-like nature that is expressed later on by Einstein. Einstein proposes the dual nature of light, and he states light is wave-like and particle-like. And if we shine light of a specific energy, a photon or a quantum of light is shined on a metal surface, then it will absorb that energy and an electron is released. So we have light coming in, that's the wave-like portion, and the particle-like portion is the electron that is released. When an electron in an atom, this is an atom positively charged, and we have the electrons out here, and let's say any electron that it's in the lowest energy level it could possibly be, which is referred to as the ground state. If this electron gains energy, it's going to jump to a higher energy state, which is referred to as the excited state. As it comes back down to the ground state, it's going to release energy in the form of light, specific light. Now, if we take that light and we pass it through a prism, we're not going to see the rainbows of the colors, but we're going to see specific bands of color, and that is referred to as the line emission spectra or atomic emission spectra, which is like the fingerprint of an atom. This is an example of the line emission spectra. Basically, we see on top, right here, sunlight, and you can see all the colors of the rainbow. You could see red, orange, yellow, green, blue, indigo, and violet. Now, if we look at a specific element, for example, hydrogen. Hydrogen, if we take the light produced by hydrogen, pass it through a prism, we're going to see specific bands of light, the red, the blues, the violets, and notice the wavelength for these are going to decrease here for violet. Notice 400, 500, 600. We see helium has a completely different pattern, line emission pattern. So these are referred to as the line emission spectra or atomic emission spectra, and they act as the fingerprints of the element in recognizing that element. Notice this is helium, and this is the line emission spectra for mercury. It is specific for each specific element.